Hey everyone, so far we have talked about atoms, we've talked about electrons and bonds and polarities that are generated because of differences in electronegativity, and we have gone on to talk about types of structural drawings. We used Lewis structures to bookkeep our electrons and to assign formal structures, formal charges, I mean. And we have learned how to various ways to draw organic structures, finishing and learning how to use skeletal structures, which is really what we'll use the most of in this class. So far, all of our structures, though, have been drawn as though they were planar, right? So we had methane like this in our Kekule structure. And it looks like all those bonds are lying in the plane of the board or the paper or whatever. So what we'd like to do now is look a little bit more about the three-dimensional shape of organic molecules, and then once we've done that, figure out how we can use the available orbitals, the s and the p atomic orbitals, in order to match those three-dimensional shapes. All right, so like I was mentioning on the previous slide, something like methane, like this, we've been drawing it like it's all in one plane, but is there any reason to believe that that's what the shape should be? Not really. And in fact, it doesn't really make sense for this molecule to be planar like this. We can use a simple concept of just thinking about how each of these pairs of bonding electrons, right, this pair, are all negatively charged, and so those electrons are going to want to get as far apart as possible. All right, and so being here at 90-degree angles, it's not as far apart as they can get. In fact, if we change the shape of that into this shape right here, okay, I'm going to use some different types of bonds here. I'm going to use a wedge and a dashed line to draw this structure right now. So, do you remember what the wedged and the dashed lines mean? Okay, so the wedged bond here is supposed to be a perspective drawing like you would do in an art class, right? And so things get smaller as they go farther away, and so this wedge is getting fatter as it gets to the atom, so that means it's pointing out of the plane, so it's pointing out towards us. Okay, and the dashed line is supposed to be fading away as it goes toward the atom, so this is pointing in. Okay, so what kind of a shape are we trying to draw here? So this molecule is drawn, what we're trying to represent at least, is a tetrahedron. So a tetrahedral shape. And if this molecule can adopt a tetrahedral shape, this bond angle can go from 90 degrees up there to 109.7 degrees. All right, so that bond angle is opening up. The electrons are getting farther apart, and so this is becoming more stable. All right, so methane, in this case, can adopt this tetrahedral shape, makes it more stable. All right, what about this next one, C2H4? What kind of a molecules that's going to look like? So if we figured this out, this would be C2H4. Okay, this is ethene. This is methane. Oops, methane. Okay, this shows you again something about our naming. A and E is all single bonds, and E and E, what do you think that would stand for? So that means that we've got a double bond. Alright, so if we tried to figure this molecule out, and if we wanted to allow these atoms to get as far apart as possible around these atoms, what we would end up with is having each one of these carbons, like this, adopt a trigonal planar shape. Okay, and then at this point, these angles and these angles can be about at 120 degrees. Alright, so this is trigonal planar. Okay, so we've opened up a wider angle, let those get farther apart. And this last one, we've looked at this before, and I think I probably drew it as it actually is. This is affine. Right? And so notice that each of those carbons only has two other atoms attached, and so these angles can adopt a linear shape or be 180 degrees apart. Alright? So this statement of why this is, so the repulsion of the bonding electrons, letting them get far apart as possible, is kind of a statement of this valence shell electron pair repulsion theory, or the VSEPR theory. So here I've restated it: bonding and non-bonding electrons present in the negatively charged represent negatively charged electron density. Okay, so the difference here is they can also include non-bonding electrons, and these negatively charged electrons repel each other, and so these electron pairs are going to orient themselves to minimize this electron repulsion. Okay, so here's just a few more examples, and so let's look at, this is ammonia, right? So if nitrogen has 3 hydrogens on it, what else is it going to have attached to it? Thinking back to those generalized structures that we did last time, for nitrogen to be neutral, it would also have a non-bonding pair of electrons. All right? So we have 4 pairs of electrons around nitrogen. They're going to want to get as far apart as possible, and so this nitrogen can adopt a tetrahedral shape, which kind of gives us this bent shape if we're looking at, or this trigonal pyramid shape if we're just looking at the atoms. But if we look at the electrons, we're going to have a bond, or have a pair of electrons going up like this. Alright? So this, the geometry around the nitrogen with its electrons would actually be tetrahedral. Okay? Here's, we did this one before. This is formaldehyde. Right? We drew this structure like this. The double bond on the oxygen, 2 non-bonding pairs on the oxygen. So what would the geometry be around the carbon and around the oxygen in order to allow these electron pairs to get as far apart as possible? Okay, so we're going to end up with a trigonal planar arrangement around each of these atoms. But we have this pair over here. I'll show you about these little loops that I'm drawing here in a minute. Alright, and so these angles would all be around 120 degrees. Okay, just letting things get as far apart as possible. Alright, this structure here, this is hydrogen cyanide. Okay, so don't breathe this stuff in. It's very poisonous. So we figured out the whole Lewis structure here. We'd have the carbon in the middle, triple bond to the nitrogen with another non-bonding pair of electrons on the nitrogen. So again, this is kind of like ethine or acetylene that we saw in the last slide. This carbon right here has a hydrogen and it has a nitrogen. So in order for those to get as far apart as possible, this could arrange at 180 degrees, and then we'd have this non-bonding pair. This would be 180 degrees too. These would all be linear. All right, so we can predict some of the shapes of these molecules just based upon this simple concept of electron pairs orienting themselves to minimize electron repulsion. Okay, so I think this is it. So this presents us with a bit of a problem or a challenge here, though, because now we have to consider bond angles of 109.5, 120, and 180, all right? But all we have to work with are the s and the p orbitals, okay? So here we have the 1s and the 2s orbitals. Remember that those orbitals are both spherical, right? So there's no directionality to these at all. Right? So they can't really be used to make any specific type of bond angle. Now the 2p orbitals, remember we have 3 of those, and they differ in that they orient themselves in different directions, but they orient themselves along the axes of this Cartesian coordinate system. All right, so we have the 2px goes along the x-axis, the 2py goes along the y-axis, and the 2pz goes along this z-axis. Okay, so these do have directionality, but they're only at 90-degree angles. And did we see any of those molecules with bond angles of 90 degrees? No, we didn't see any like that, right? We had 109.5, 120, and 180. And so how are we going to use these s and p orbitals to make bond angles which we observe? All right, so before we get into that exactly, let's just think a little bit more about what happens when we form a bond, okay, and bond lengths and things like that. So when we form a bond, we're going to bring 2 atoms together. Here we have just 2 hydrogen atoms, right? They each have their single electron. We're going to bring those together and form a covalent bond, all right? This graph down here shows the energy, all right, versus the internuclear distance, the distance between the 2 nuclei. All right, so in fact, this graph is kind of backwards to what we were showing up above. So if here's the far apart out here, this is a large distance. All right, and right here is the energy of just the hydrogen atoms. All right, so as we come together, notice that the energy starts to go down, all right, because there's an attractive force between these 2 hydrogen atoms. Remember, each of those atoms is going to be more stable if it can get a full electron shell. Right, so they are going to be attracted. This is an attraction here. Right, they're gaining stability by pairing up their electrons. All right, but it gets to a certain point. It's not just that you get closer is good and always more close is better, but if we get close enough, then look at this. The energy goes shooting out of the roof. Right, so why would that be? Okay, So if we bring these atoms too close together, then the nuclei, or the the protons in the nucleus, right, are going to start to repel each other. Okay, so here we have a nuclear repulsion. Okay, so there's going to be some equilibrium point, some point of maximum stability where this attraction is balanced by repulsion, right? And so for a hydrogen-hydrogen bond, it turns out that this distance right here, 0.74 angstroms, is the best distance. That gives us the lowest energy, which makes it the most stable, all right? Now, if we look at these two p orbitals, they're going to overlap like this. And if we looked at it from the end, it would just look like a sphere, right? Or not a sphere, it's more of a cylinder, right? Cylindrical. Okay, so cylindrical bonds are what we call sigma bonds. Okay, here's sigma right there. Okay, so we're going to see a lot of sigma bonds in organic. Alright, so now that we know how to make an individual bond, let's look at how we could get these geometries. Alright, so we're going to use a model of bonding, a model of orbitals that was generated by Linus Pauling. Pauling was an amazing guy. He's one of the only, if not the only person who won the Nobel Prize in two different areas. So he won the Nobel Prize in chemistry, and he also won the Nobel Peace Prize. I was lucky enough to see him give seminars 2 times when I was in graduate school. When he won the Nobel Prize, it was based upon a series of lectures called the Baker Lectures, and he gave this series of lectures called The Nature of the Chemical Bond. And he gave those, the Baker Lectures, at Cornell University, where I was in graduate school, and he came back 50 years later and gave a repeat of those lectures, and I was able to be there for that. That was really exciting. Him and some other Nobel laureates were all in the audience and all like kind of giving each other a hard time, and it was kind of funny to watch. All right, so Pauling came up with this model of bonding of orbitals in order to account for the shapes. Okay, so in this model, it's called hybridization. What it describes is atomic orbitals, so those are the s and the p orbitals, can be mixed or hybridized to create new hybridized orbitals. Okay, so the hybridized orbitals are formed by mixing the atomic orbitals. The new hybridized orbitals orient themselves to minimize the electron repulsion. Okay, so if we think about methane, all right, what do we need? How many equal orbitals do we need for those orbitals to orient to the corners of a tetrahedron? Right, so we need 4 equal orbitals. Okay, gonna do this. All right, so here's all of the orbitals that we have. All right, and for carbon, right, we could put our electrons in here. We have 1 electron here in the 1s. Okay, we have 2 electrons there. We have an electron here. So if we were going to do this, we'd pair those up. And how many more? We have 2 more electrons. We got 1 here and 1 here. Okay, so we don't really have to worry about the 1s, right? Because they're not valence electrons. So all the bonding is going to take place in the valence electrons. So we have a 2s and we have 3 2p orbitals. All right, so what's going to happen is we want 4 orbitals, and so we're going to mix 4 orbitals. We're going to mix the 2s and all 3 of those 2p orbitals. Okay, so like this. We're going to mix these, or what we call hybridize them. And we're going to end up with 4 new orbitals that are all going to be the same energy. Okay? These are all formed by an S and 3p. So we're going to call these S. We have 1 part S, and we have 3 parts p. So these are all called sp3 orbitals. All right? What we didn't talk about before is in the p orbitals, notice that we have these 2 different colors. All right? Now the colors kind of, they represent different phases. Okay? Different colors equal different phases. And the phases we can think of as being not charges, but the differences in a plus and a minus, say in a mathematical function. So if we had something like a sine or cosine, we'd have something like this, and we might have plus and minus down here. All right, so it's just the sign of the function. All right, so the way sp3 orbitals look, if we're going to draw these, are going to look a lot like p, but they're going to be bigger on one side than they are on the other. Okay, so this is the sp3 orbital, and we have 4 of them, so they can orient themselves as far apart as possible along the corners of a tetrahedral. So this usually takes a little more artistic skill than I have. Okay, so this one will go out in the front, and this one will be kind of back behind, out in the front over here. Okay, so we have 4 sp3 orbitals. All right. When we place our electrons in the sp3 orbitals, the new hybridized orbitals, notice that all those orbitals are the same energy. So we can just put 1 electron in each orbital. Okay? So then we essentially have 1 electron in each of these orbitals ready for a bond, and they're getting as far apart as possible, right? So for methane, right, we're going to just have a hydrogen here with its S, hydrogen here with its S, hydrogen here with its orbital, its electron, I mean, and like that, right? So each of these bonds are made between an sp3 hybridized orbital on the carbon and the 1s orbital on the hydrogen. So again, they're going to be cylindrical. So these are all called sigma bonds. Okay? So we've got 4 identical orbitals going to 4 hydrogens. All right? Those bonding pairs here now are orienting themselves as far apart as possible. Okay, so I think I put all of what we needed on that last slide already. Got ahead of myself, too excited here. And so again, here's the computer drawing of what that orbital looks like. Okay? all four of those can orient as far apart as possible. The reason why we get one lobe bigger than the other is we can think about here, look at, we have two green phases adding together, so they're adding on one side, and we have a mismatch of color over here, and this is like subtracting over here. All right, so one side gets smaller, one side gets bigger. Okay, so we could draw that out again. Well, we already drew that. Okay, so what if we, well, here's another example of using the same type of orbital. So here's in the bonding for ethane. All right, so we notice that each of these carbons, it has 4 single bonds. So we need 4 orbitals to make those single bonds. Okay, and those orbitals are going to orient themselves as far apart as possible. All right, in order to get 4, then we make sp3 hybridized orbitals. Okay, and so here is the drawing down here. All we're showing in this case is just the big lobe. So they've left out the little lobe on the back. And we see that we have one sigma bond, sigma bond, formed by 2 sp3 orbitals. Okay, they're overlapping end-on. And then we also have these other sigma bonds formed between the carbon sp3 hybridized orbitals and the hydrogen hydrogen 1s orbital. Okay, so let's look at ethene. Okay, so do you remember the structure of ethene? All right, so ethene, remember, was trigonal planar to get those bonding electrons as far apart as possible. Remember, these angles were around 120 degrees. So what do we need as far as orbitals go for these carbons? Okay, so do we need 4 separate orbitals? So 4 equivalent. Notice that these carbons now are bonded to 3 other atoms. Carbon bonded to 3 atoms. Okay, so we need 3 orbitals. Okay, we have an extra bond. We have second half of our double bond, but I'll show you how that gets generated in just a second. Okay, so we need 3, we're going to get 3 sigma bonds. Okay, if we only need 3, then we only need to use 3 of these 4 orbitals. All right, we're always going to use the s because that's the lowest energy. And so in this case, we're going to mix the 2s and 2 of the 2p orbitals. All right. So the new orbitals, since there's 2 parts p and 1 part s, it's going to be about 2/3 of the way up. And we're going to get 3 identical orbitals. All right, and these 3 are going to be called sp2 orbitals. But we have that 1p orbital that we haven't used, so that's still left over. Okay? These new sp2 orbitals look kind of like the sp3 hybridized orbitals that we drew before. And as far as my artistic skills go, they look the same. Okay? They have a large orbital or lobe and a small lobe. Okay? The difference here is going to be their orientation. Okay? So we can have a carbon that now has 3 of these orbitals that are going to orient themselves at 120 degrees apart, like this. Okay? I have 1 orbital in each one, 1 electron in each one. Okay, so let's look at how this would show up in the molecule. All right, so here we have this drawing up here. we have, again, we're drawing the sp2 hybridized orbitals without the back. So, right, each one would have a little lobe going back like this. But here's the big lobe, and they're forming sigma bonds. We have the carbon-carbon sigma bond in the middle, and we have carbon-hydrogen sigma bonds, just like we did before. So remember what we have left over now. When we did sp2, we only used 2 of the p orbitals. All right, so we have 1 p orbital left over. Right, and that p orbital is going to show up right here. It's perpendicular to the plane of the sp2 hybridized orbitals. All right, so each of these carbons has a p orbital, and those p orbitals can overlap and interact in a side-by-side manner. All right, and this is called a sigma bond. So this is a separate type of bond. Okay, so the double bond then is made up of 1 sigma bond and 1 pi bond. So that's what makes the double bond. Here's the one that shows them all on a single structure. So here's some angles. So notice that the bond angles are not exactly 120 degrees. It has a lot to do with the size of the atoms. So if we look at the angle between this hydrogen and the carbon, this group over here is much bigger than the hydrogen, than this hydrogen. So this bond angle opens up, and this one gets a little bit narrower. So 121.7 versus 116.6. You don't need to know these exact numbers or anything. We just want to know that they go at about 120 degrees. All right, so when we look at the atoms themselves, they're all going to be in the same plane. All right, so this whole molecule is planar. All right, so let's look at the scenario then. Okay, so remember this molecule, C2H2. So this was ethine or acetylene, H, and we have this triple bond. Okay, so now this carbon needs 2 sigma bonds. So it needs 2 orbitals. Okay, so if we only need 2, then we're going to use the s, but we're only going to use 1 of the p orbitals. Okay, and so we're going to create some orbitals that are called sp hybridized orbitals. Because it was 1 part s and 1 part p, it's going to be just 50%, right in the middle of those two. We're going to have 2 of these. These are going to be sp, and we're going to have 2 p orbitals left over. Okay. Again, just like before, the sp orbitals look similar in that they have 1 big lobe and 1 small lobe. And the difference now is that they're going to be 180 degrees apart. All right, so each one of these, we could draw this out, is going to have this orbital here. There's a sigma, and this is the other side. All right, and these are going to go to the hydrogens. Okay, so these aren't just p orbitals, right, on the carbon here. I'm just showing the big lobe of the sp hybridized orbital. So one of those is making a sigma bond to the other carbon. The other one is making a sigma bond to the hydrogen. All right, so then we have two p orbitals left over. So one is going to go like this. Okay, and those can form a pi bond. And then the other pair, the other p orbitals are going to be going in and out of the plane like this. So those form a second pi bond. All right, so when we form a bond, we have a combination of 1 sigma bond plus 2 pi bonds. All right? And the angle is 180 degrees apart. All right, so this shows the sp orbitals that are forming the sigma bond there, and here's the 2 pi bonds here. Notice that they're essentially 90 degrees apart. And in this case, we basically get this linear molecule for ethine. All right? So, in this lecture, what we've done is we started with our planar molecules that we had drawn from the Kekule structures, and we put them into 3 dimensions. We understand now that the bonding electrons and the non-bonding electrons repulse each other, repel each other, and so they're going to orient themselves to get as far apart as possible. All right, and so if we have 4 pairs of electrons, then they're going to go to a tetrahedral. If we have 3 pairs, they're going to go to a trigonal planar, and if we have only 2 sets of electrons, they're going to go linear, and this is described by this VSEPR theory. All right, we learned too how we can mix together s and p atomic orbitals to give us either sp3, sp2, or sp hybridized orbitals, which allow us to explain the different molecular geometries. All right, so next time what we'll do is we'll learn some generalizations about these so we can look at any structure and quickly identify the hybridization and the numbers of sigma and pi bonds, and then we'll go on and we'll look at some just general trends in structures, and we'll be done with this chapter. All right, bye.